Hello, my name is Megan, and today we are going to talk about how action potentials propagate along excitatory circuits in comparison to how action potentials propagate along inhibitory circuits. A circuit is the pathway of communication between cells. We will begin with the propagation of an action potential along an excitatory circuit. As the first neuron releases glutamate into the postsynaptic cleft, the neurotransmitter glutamate binds to ionotropic AMPA receptors, causing the receptor to open and allowing an influx of sodium cations into the presynaptic neuron. With influx of positive charged ions, the membrane potential of the presynaptic cell depolarizes, and this is called a graded excitatory postsynaptic potential. When the second neuron receives enough excitatory postsynaptic potentials to reach threshold at approximately -55 millivolts, an action potential will be triggered in the second neuron. The action potential begins with the voltage-gated sodium channels opening, allowing sodium to enter the cell at the site of the axon hillock. Influx of sodium causes the rising phase of the action potential through depolarization. The voltage-gated sodium channels close when the membrane potential reaches approximately 40 millivolts, and the voltage-gated potassium channels open, causing efflux of potassium cations out of the cell. This triggers the falling phase, where the cell repolarizes. The voltage change of an action potential can be seen in the graph here, which depicts voltage in millivolts on the y-axis and time in milliseconds on the x-axis. As you can see, there is a rising phase, a falling phase, and an undershoot phase, where the membrane potential temporarily falls below resting membrane potential. This occurs because it takes voltage-gated potassium channels longer to close, allowing more efflux of positive charged potassium ions out of the cell. Once the voltage-gated potassium channels fully close, the membrane potential stabilizes, again due to potassium leak channels and the sodium-potassium pump. As you can see in the image, the action potential continues to propagate along the axon of the neuron until it reaches the axon terminals of the second neuron in the circuit. This causes the voltage-gated calcium channels to open, allowing calcium cations to influx into the cell, activating synaptotagmin and causing vesicles to fuse with the cell membrane via V snares and T snares proteins. Vesicle fusion releases more glutamate into the synaptic cleft, which can then bind to ionotropic AMPA receptors on the next presynaptic neuron, or the third neuron in our excitatory circuit, and this allows the process to begin again. Now, we will look at the mechanisms of an inhibitory circuit. What happens if the first neuron in the circuit releases neurotransmitters that bind to receptors, initiating an inhibitory response in the second neuron? For our purposes, the first neuron will release glutamate into the synaptic cleft of the presynaptic neuron, or second neuron in our circuit. This time, the glutamate neurotransmitters bind to ionotropic GABA receptors, GABA A receptors, which open chloride channels, allowing chloride anions to influx into the presynaptic cell. In response, the receiving cell hyperpolarizes, falling below the cell's resting membrane potential of approximately -70 millivolts. This voltage change can be seen in the graph depicted here. These inhibitory signals, or inhibitory postsynaptic potentials, do not allow the second cell to reach threshold potential, and no action potential is fired. Because the second cell is unable to fire an action potential, no neurotransmitters are released to signal the next neuron in our circuit, and likewise, no action potential can be fired in the third neuron. That concludes my talk today on action potential propagation along excitatory circuits versus inhibitory circuits. I hope you enjoyed. See you next time.